Hello, I am Rakesh Nadig. In this lightning talk, I'll give a brief preview of our work, Venice improving solid-state drive parallelism at low cost via conflict-free accesses. Now let's look at the key problem that we address in this work. In commodity SSDs, multiple flash memory chips are connected to the SSD controller using a shared channel. I/O requests in data-intensive workloads attempt to simultaneously access the flash chips using a single path, which cause path conflict in SSDs. Path conflicts cause I/O requests to be transferred serially on the shared channel, which limits SSD parallelism and reduces overall performance. Next, we look at the delay caused by path conflicts. If two read requests target flash chips connected to the same channel, they experience path conflict. And several parts of the read requests are served serially because of the single shared channel. Next, we look at two read requests that target flash chips connected to different channels, and they can be served in parallel as we see in this timeline. And this saves a lot of cycles. Path conflicts increase the average I/O latency by 57% in our experiments on a performance-optimized SSD. The performance overhead of path conflicts increases by 1.6 times for high I/O intensity workloads. Next, we look at some prior approaches. We have a typical multi-channel shared bus architecture for baseline SSD. Packetized SSD increases the channel bandwidth by 2 times. These approaches do not provide path diversity for flash chips. Packetized network SSD introduces vertical channels to increase the path diversity, and network on SSD introduces an interconnection network of flash chips. These approaches do not effectively utilize the path diversity, and they incur large area and cost overheads. Our goal is to fundamentally address the path conflict problem in SSDs by increasing the path diversity at low cost and effectively utilizing the increased path diversity for communication between the SSD controller and flash chips. To this end, we propose Venice. Venice has 3 key components: a low-cost interconnection network of flash chips in the SSD, conflict-free path reservation for each I/O request, and a non-minimal fully adaptive routing algorithm for path identification. Let's look at the architecture of Venice. Venice has an interconnection network of flash nodes, which are connected using bidirectional links, and each flash node consists of a flash chip and a router chip placed next to it. Venice provides increased path diversity at low cost, and existing flash chips do not require any modifications in Venice. Now let's look at path reservation. Venice uses a small scout packet to reserve a conflict-free path for each I/O request, and path reservation eliminates path conflicts by enabling conflict-free I/O transfer. In summary, Venice mitigates path conflicts by efficiently utilizing the path diversity of the SSD interconnection network. Venice significantly improves performance over prior approaches. Venice reduces energy consumption by 46% on average over the most efficient prior work, and the benefits of Venice come at a low cost and requires no changes to commodity flash chips. To know more about Venice, please visit us at Session3B on 19 June at 4 p.m. and read our paper. Thank you.